Good afternoon. I hope I'm audible, right?
Yes, sir.
Okay. So let us. Please mute yourself. Please mute yourself. Is the presentation visible now?
Yes, sir.
Good. Okay. So we have been discussing on the dynamic binding polymorphism, where different classes on a hierarchy can behavior. So we will continue on that. Now, first, what we want to understand better is the meaning of static and dynamic type, or the meaning of static and dynamic binding. Right? The static type of the object is a type that is declared for the object while writing the code. So here below you have a class A, and we have another class B, which is inherited from A. This is public inheritance, so this is pure hierarchy. And can you hear me? I am hearing some.
Sir, there are disruptions in the audio stream.
Sir, your voice is breaking.
Oh,
Sir, now we cannot hear you at all.
can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, I was having some problem. I don't know what's wrong with this Teams. So we can share the presentation. I hope you can see that.
Yes, sir.
Okay. So the static type of an object is a type that is declared for the object while writing the code. A and B is A. Now, if I write A star P, that is a type of P, is what you see in the code, which is a pointer to class A. So it is a pointer to a class A type of object. That is what the compiler gets to see. That is a static type. Static because it is happening at the compilation time, whose other reference is often static time. The dynamic type of the object is determined by the type of the object to which it currently refers. This is different. So in P now, I'm making an assignment by dynamically creating an object of class B. So the object point that I get from this new B is a pointer to an object of class B, whereas P is a pointer to an object of class A. So the static type of P, what the compiler gets to see, is A, whereas the dynamic type of P, that is the type of the actual object that P is pointing to, is B. The compiler does not see the dynamic type, because you can understand that this could happen in terms of the code flow anywhere, anyway. You can get that pointer from some other pointer and so on, right? So that is the basic difference between the static and the dynamic type. And this difference in C++ can happen only in terms of the object class hierarchy. It is not possible in other cases, because you have seen that casting pointers of any other kind can at times be done forcibly, but actually are not semantically consistent. I will make a reference to, you had an extensive lecture by Professor Abir yesterday on Python. Python is a language which is completely dynamically typed, where the compiler does not consider any type at the compilation time or at the code, but it tries to derive the type based on the object it is actually dealing with. C++ does not have that flexibility. It is statically typed, but in this particular case, the pointer P has a dynamic type which is different from its static type. Now, based on this, we have two concepts. One is called static binding. When a function invocation binds to the function definition based on the static type of the object. Yeah, I know the static type of the object, and I invoke a function. The particular function which we
Sir,
get.
your voice is not clear.
My voice is not clear?
Understandable. Yeah, it is not
Yes, sir. There
understandable.
is so much voice disturbance in your.
Okay, so let me again disconnect and come back. What else to do? Can you hear me now? Hello?
Yes, sir. Yes, sir, we can hear you.
Is it clearer?
Better.
Okay, okay. We'll go with that for now. Please mute yourself. So you're back to the slide. So static binding is when the function invocation binds to the function definition based on the static type of the object. I know the static type, compile time type. This is done at the compile time, and from that I resolve which function will be invoked. So normal function calls, overloaded function calls, overloaded operators are all static binding. Dynamic binding, which is called late binding, is when a function invocation binds to the function definition based on the dynamic type of the object, not on the static type. So static type could be something different, but it will decide on which function to call. We say which function to bind depending on the runtime type of that object. So virtual functions are examples of such dynamic binding or late binding. So I talked about this earlier also, but I'm just making it more explicit. So this is a clear example of static binding. Class D is derived from class B. B has a function f and D has a function g, which is a new function. So naturally, by inheritance, D also has a function b, which is the function defined in the class B. So if I invoke b dot f, I get the f function of b. If I invoke b dot f, I also get the B function of F, because the compiler statically knows that the type of D is class D, which has inherited a function F from B, which is B colon F, and it binds to that function. I have D dot G, we'll call D colon G because it's an added function. So this is, I can do overriding. When I do overriding, again, I have static binding here, where the function F in D has overridden the function F in B. So that function F in B is now masked. That cannot be called. So if I call B dot F, B colon F is called, because statically I know the type of B is class B. Similarly, if I do D dot F, now D colon F is called, because I statically know that the type of D is class B. It masks the base class. This is what, again, we have seen, that if we do inheritance and also do overriding and overloading, then this is what happens. I have F and G, D inherits both of them and calls all calls by B or D goes to the B class functions. But if D inherits and overrides F int, then when I call D dot F3, it calls D colon F int. If it overloads the function F from B, that function gets called when I call D dot F with red, and so on. So this is the basic static mechanisms that we have seen. Now, since if I override a function, then if I overload a function, if I overload a function, then the original function in the base class gets hidden. So if I have a class A and B is a, then A has a function F. So I have inherited that, but I have overloaded with F int. Right? So if I overload it with F int, then I will not be able to call with the B object, with the object B, I will not be able to call B dot F with parentheses. Just, without any parameter, because that function has got hidden. But of course, we can work around that by doing the using construct we saw earlier also. I can say using A colon F, which will mean that B now has two versions of F function. One is A colon F, which is coming through using, and the other, which is the overloaded version that it has added. So this is the basic mechanism. Now you dynamic binding. Dynamic binding is here. We have two classes B and D. Both have F. So D has overridden F, and therefore, if I try to call, let's say, now if I try to call B with the, now if I try to make a call through the pointer, let's say I have two objects B and D, and I have a pointer to class B, and I do P pointer F. If the object being pointed to is B, compiler knows that P is of type B pointer, base class pointer. So it will immediately call B colon F. If I set the pointer to a D class object, even then P pointer F will call the B class function of F, because it is statically resolved. Statically, it knows that P is a pointed to a B class object, so it will call the B class function. This is the basic static non-virtual mechanism. Now we can make it virtual or dynamic by writing a keyword virtual before the function signature in the base class. And then I override it in the derived class. And I write exactly the same code. Nothing has changed. I have written the code virtual here. Then what happens? P is pointing the pointer of B class. Compiler knows that statically. If I do p pointer f, when p is ampersand b, that is the actual object is a b type object, it still calls the function f of class b. But if I set p to the address of a d class object by ampersand d, then p pointer f, it statically it would say that it should call b colon colon f, but because of this virtual keyword, this will now be dynamically resolved based on the type of the actual object being pointed to, which is a d class object, and it will call d colon colon f. This is the basic idea of dynamic binding. And over a class hierarchy, when you override functions, this is the basic difference between static binding and dynamic binding. So this is something of an example we saw earlier. We can quickly go through again. We have f and g, two functions. You can clearly see f is non-virtual, g is virtual. And then you have a pointer to B class, two pointers to B class, two references to B class set to the respective objects, which are basically upcast examples. Now, if you call the functions by the object, which you can always do, it is always statically bound. It will always call the function of the class to which that object is an instance of. So they are all statically bound. But if you call through the pointer, then the non-virtual function, particularly the case to see is the case of PD pointer f. That is interesting. Here, if you have a static binding, then PD is a pointer of type class B. So it calls B colon colon f. But if you do PD pointer G, this is a virtual function. So knowing that PD actually is pointing to a D class object, it will call the D class function, which is D colon colon G. So that is the basic difference. Similar thing will happen if you use reference also. But if you directly use object, it is always static. There's no difference in terms of the behavior of virtual and non-virtual functions if you are calling them on the object. But if you are calling them through pointers to the base class or through references to the base class, references of the base class, then the resolution for virtual function will happen based on the actual object being pointed to or the actual object that is referred. Right? So this is what is called a polymorphic type. Dynamic binding is possible only for pointer and reference, as we have said. It can be overwritten and so on. So this is any class containing a virtual member function by definition or by inheritance is called a polymorphic type. A hierarchy may be polymorphic or it may be non-polymorphic. And as we'll see that in usual design, a non-polymorphic hierarchy usually will have not much value. So this is the rule of polymorphism. Look at this slide very carefully, slide 12, module 27. You have a base class A, which is not derived from any class. So this is a root class. It has three member functions, f, g, and h, of which g is virtual, other two are non-virtual. Then you derive B from A and overwrite all three functions. Now, as you overwrite F, which was non-virtual, F continues to remain non-virtual. As you overwrite G, note that you have not written virtual here explicitly. But G is virtual in A, so once it is virtual, in all its subsequent inheritance down the hierarchy, it will remain virtual. Once a virtual, always a virtual down the hierarchy. So even though I have not written G to be virtual, it will be treated as virtual. It will be dynamically bound. And then I have overridden H, where it was non-virtual, I have made it virtual. So what has happened in A, it is virtual, but H in B is, in A, it is non-virtual, I'm sorry. In B, I have made it virtual. So I can convert a function non-virtual to virtual at a level of the hierarchy, but I cannot do the reverse. Once a function is virtual, down below the hierarchy, it is always virtual. And then I have class C, where I have again overridden everything without doing any virtual or anything. F, it was non-virtual in B, so it remains non-virtual. G and H were both virtual in B, so they will remain to be virtual. So now if I make these calls, I have created an instance of class C, and I have put that pointer to a pointer of class B. And then I have another pointer P of class A to which has been initialized with Q. So both P and Q point to an object which is an instance of class C. But P is of static type A pointer, Q is of static type B pointer. Now I make 3 calls with P, F, G, and H. Now what happens? P is a pointer. So it goes by the virtual, non-virtual part of A. So P pointer F obviously is A colon colon F, because that is a non-virtual function, so that will get called. What is P pointer G? P pointer G is virtual in A. So it will call the function of the object that it is currently pointing to. It is currently pointing to a C class object. So P pointer G will call C colon colon G, because G is virtual here.
Excuse me, sir.
Yes?
I think your screen is frozen. We can see slide number 9.
You can see slide number 9.
Yes.
Fun things keep on happening. I'm getting exasperated with this. Can you see slide 12 of module 27 now?
Yes.
Even if it gets frozen, I'll keep on saying what is the slide number. You have the slide deck, so you can just refer to that. But tell me when it gets frozen again. So when I do P pointer H is non-virtual in A. So like F, P pointer H will also called A colon colon H. Okay, so that's. Now consider invoking the same set of functions with the Q pointer. Nothing has changed. The object has not changed. The functions you are calling are not changed, but the type of the pointer on which you are calling is different. It is now a B class pointer. So it goes by the rules of B class. F is non-virtual. So Q pointer F is non-virtually resolved, statically resolved. So it is B colon colon F, because B has overridden F. Now, if you call Q pointer G, it is a virtual function. So it is resolved based on the type of the object, which is C. So it calls C colon colon G. But this was, so the first F had a difference because it is statically bound. G did not have a difference from P. If you do Q pointer H, now in class B, H is a virtual function. So the call will depend on the dynamic type. So it will now call C colon colon H. Mind you, earlier it was calling A colon colon H because H was non-virtual in class. Right? So this is one slide which you can keep and refer to in case you have get into some confusion as to what is virtual non-virtual doing, but this clearly tells you that. And you can create a completely parallel set of calling conventions and the same results if instead of pointer you use reference to this object that is just constructed, the object of class C. Reference two references, one is reference of type A, class A, and reference of type class B. You call through the references, you will get the same method. Okay, so that was the basic static and dynamic binding and the polymorphic type. So I'm moving on to the next module, module 28, where I will talk about a new concept first, which is a virtual destructor. And then we'll bring in pure virtual function and abstract base class. Our discussion starts on slide 4 of module 28. I hope you are being able to see that slide. Right?
Yes, that's visible.
Okay. So just look at this example. It's a simple example, but it has very deep consequences. I have a class B with a data member int data. The class B has a public constructor which initializes data and prints a message to indicate to us that the constructor has been called. It has a destructor which just prints a message to say that the destructor is called, and it has a virtual print function which prints the data. Inherited from that is class D, which has a pointer to int ptr. It has a constructor of D which takes these values, two integer values. With the first one, it creates a base class instance of B with D1, which needs one integer. With the second integer, it dynamically creates a integer object and places that pointer to the ptr member of class D. Sends also a message saying the constructor of class D has been called. Similarly, the destructor of class D prints a message to tell us that it's been called. And since I had done a new, I clean up when I'm cleaning up class D object, and I delete that pointer. In the overriding of print function in class D, I directly call the B class function to print the B class member, because in class D I cannot access data underscore, it is private. So I call the B colon colon print function here to call the base class function and then print out the pointed value in this class. Right? So this is a simple design of the class. I create two instances, one of class B with value 2, one of class D of value 3, 5, and let two pointers P and Q, both of the base class type, point to them. I do P pointer print. Naturally, it calls B colon colon print. I do Q pointer print. Naturally, it calls D colon colon print. Then I delete these objects to clean up the objects that I had created, and I return. Right. So I apparently have written a perfect, clear code in terms of this. Right? Now let's see the output to understand what's actually happening. I do new. So on class B, so the constructor of B is called, that is shown here. I get that message. Then I try to construct an object of class D. It has to first construct an object of class B. So again, the constructor of class B is called, and I get that message. Then it actually completes the construction of class D and I get that message. Then I do p pointer print, which calls b colon colon print, prints the data 2 that I had placed, which is right. Then I do q pointer print. It calls b colon colon print, goes there, prints the data, which is 3, and then prints the data pointed to by class D, which is 5. This is. Then I do delete p. Delete p, what should it do? It should delete the B class object. So it should call the destructor. I get the call to the destructor. Then I do delete q. When I do delete q, I get the call to destructor of class B, but the destructor of class D is not called. This message is not printed, which means that the pointer that I had allocated by doing this new is not cleaned up. Why did that happen? The destructor of D, type D, is not getting called. What is the problem? The problem is simple. The problem is delete Q knows that Q is a pointer of type B. So delete Q knows that it has to call the destructor of the class it is pointing to. So it comes to this destructor and calls it. But what should have happened is, so this delete is making a call which is statically bound. And statically, Q knows that it is a B class type pointer. So it is calling the B class destructor. But the dynamic type of Q is different. It is D. So it should have called the destructor of D first, and that should have called the destructor of B and so on. But that will not happen because Q is binding with the destructor with a static binding. So what do we need to do? Let us go to the next slide. I'm on slide 5, module 28. All that I have done is I have written virtual in front of the destructor. So I said destructor itself is a virtual function. It has to be dynamically bound. Now what happens when I do delete Q? It knows that it is a B class pointer and it has to invoke the destructor of the class whose object it is currently pointing to. It will use a dynamic binding. So if it uses dynamic binding, Q is pointing to a D-type object. So it calls the call to the destructor here actually gets dispatched onto D colon colon tilde D, the destructor of D, as you can see here. Now as it calls destructor of D, that in turn will call the destructor of B, because that's the protocol of the destructor calls, that it keeps on going up till the base is reached. So D will get destructed, then it will come and complete the destruction of its own pointer which it created. So this gets cleaned up. And as we get the destructor of D, type D, is being called. So if you are creating a virtual hierarchy, which means that if you have at least one virtual function in your root, so that you want to use dynamic binding, it is absolutely necessary to make the destructor of the base class virtual. And that is what is known as a virtual destructor. Without that, only what was happening, if I go back to the earlier slide 4, module 28, then what was happening is in terms of the object D35 that I dynamically created, only the base class part is getting destructed. The derived class part, the additional pointer, is not going through the destruction. So kind of this is known as the problem of slicing. I'm on slide 6, module 28. As if you are slicing out the base class part from the whole object. Just destruct that part. So if the destructor is not virtual in a polymorphic hierarchy, it leads to slicing, which is a very, very serious problem and affects the quality of your whole software very significantly. So the basic guideline is, if you have a polymorphic hierarchy, the base class destructor has to be virtual. The destructors of other classes may or may not be explicitly said to be virtual, because once you make the base class destructor virtual, by the rule that we have seen earlier, every class that is derived, specialized from the base class, either directly necessarily be treated as virtual. And wherever you point to on that hierarchy and do a call to the destruction, it will get dispatched down the hierarchy to the actual object class, which is dynamically existing at the runtime. Right? So this is the rule that you have learned. So now let us see. So we have seen a set of rules. We have seen a set of do's and don'ts, but we have not seen the real use of why we are doing all this. So for this, let us consider a different hierarchy. I'm using hierarchy of shapes, which is, if you open any book on object-oriented programming or C++, you'll probably see this hierarchy. This is most widely used. So this is basically kind of the idea is taken from that, whereas the phone hierarchy was my own creation. So here we have a hierarchy where we're saying that let us consider shapes, two-dimensional shapes. Again, I should have written two-dimensional shapes. Then I can say that a polygon is a two-dimensional shape. Similarly, a closed conic is a two-dimensional shape. There could be several others, but let us just stick to this. So I say polygon is the shapes, closed conics is the shapes. I have hybrid inheritance. Then in polygon, I say triangle is a polygon, quadrilateral is a polygon. In closed conics, I say ellipse is a closed conics, circle is a closed conic. I could continue this more. From quadrilateral, I can go to parallelogram, I can go to rhombus, from parallelogram, I could go to rectangle, from rectangle, I could go to square, so on. There are a lot of easy here. From triangle, I could go to isosceles triangle, from isosceles triangle, I go to equilateral triangle. There's a whole lot of is a hierarchy which is implicit in the domain of shapes, but we just want to understand the basic principle. Now what we need is for a graphic system, let's say, we want to have a draw function written for every class, which is to draw, given the appropriate parameters, a shape of that particular class. So I want to have a draw function which I can override everywhere to draw the corresponding shape. Now, if you think about a draw function in triangle, it will be very easy. You know the 3 points and you will draw basically 3 straight lines. Quadrilateral would be similarly. So you will probably give the points in an array or a vector in a certain order of, say, anti-clockwise direction as you move around the polygon. And given that, you will just need to keep on drawing the lines till you come back to the beginning and it will get drawn. So triangle is a special case of polygon, quadrilateral is another special case. Polygon in general can be drawn. Ellipse or circle can be drawn by the well-known Breschenum's algorithm. I do not know if you have done graphics, then you'll know. Otherwise, know that there are very easy, well-proven algorithms to draw circles, ellipse, and so on. Now the question is, so if I have to do this kind of virtual stuff, then given a collection of shape objects on my canvas, on the graphic screen, I could have some polygons, some triangles, some quadrilaterals, some ellipses, some circles, and so on, a collection of maybe 20 objects floating around on my canvas. And from that collection, I want to, for every object on that collection, I just want to call the draw function and want that object to get drawn. Which, given the virtual functionality we have seen, will be possible if we hold every object by a pointer to the root class, shapes, and just invoke draw on that pointer. Then if that object actually being pointed to is a triangle, then the draw overridden draw function of the triangle class will get called. If it is that of a circle, then the overridden draw function of circle will get called, and so on. So that's what we are trying to do. So we need to make draw everywhere to be a virtual function. So what do? We make draw virtual in the root class shapes. Then down the line, whenever I override the draw function in a respective class, then it becomes a virtual function. It remains a virtual function. Now we get into a difficulty. One, the difficulty is for polygon I know how to draw. For circle I know how to draw. For ellipse I know how to draw. For a generic concept like shape, how do I draw? Shape could be anything. So while I know that I want to call this function as draw, but I do not know what code I can write for this. What should be the body of this function? So that brings in this dilemma, or this problem brings us to a solution using pure virtual function. A pure virtual function is a very interesting function which has a signature but has no body. So any class that contains a pure virtual function is called an abstract base class. I think I will go to the example first. Then we'll come back to these definitions. I'm on slide 10, module 28. So look at this code. I have class shapes, which is obviously the root, does not inherit from anyone else. And in that I have defined, given the signature of the draw function, which does not take any parameter and returns void, and I've made that virtual. Then I specialize on this hierarchy. Polygon is a shapes. I override draw. The draw in polygon will also be a virtual function because it is inheriting from shapes. And instead of actually drawing, I'm just putting messages to say that I'm drawing. I'll say draw polygon by triangulation. Then I specialize from closed conics. Specialize closed conics from shape. I will inherit draw. Right. I'm not overriding here, because if you think about closed conics as a concept, you again do not know how to draw it. You know how to draw a circle, you know how to draw an ellipse, but in general, a closed conics you do not know, may not know how to. Look at the other part of the hierarchy. Triangle is a polygon. I override draw. It is virtual. Quadrilateral is a polygon. I override draw. It is virtual. Circle is a closed conics. I override draw. It is virtual. And ellipse is a closed conics. I override draw. It is virtual. So I have all of these. Now for shape, since I do not know how to write the code for draw, I show that by this simple syntax. I put kind of an initialization operator equal to and put 0. This tells the compiler that while I want the signature of draw to be known to the root class as a virtual function, I do not know how to implement that function. Now think about this. If I have a class where I have a function, I know this is a member function, but I do not know how to implement it. And then if I have an instance of shape created, then I'll be able to, from that instance, I'll be able to do, if I've done shapes S, I've created an object of class shape, then I'll be able to do shape.draw. But shape.draw, what will it call? I have not given a body to it. There is no actual code to execute. So this creates a new concept in the class, which is known as an abstract base class. In the sense that a class, if it has at least one pure virtual function, then you cannot create instances of that class. It just remains there as an interface, but you cannot have an object of that class. That is the reason it's called an abstract class. By legacy, naturally, we'll not have an abstract class at the leaf level. So if you have an abstract class, then you'll have something specializing from it. So you call it an abstract base class. Now, when you specialize polygon from public shapes, you inherit this draw function, virtual draw function, as a pure virtual function. So when you override, by overriding, you are saying that I'm now providing a draw function for polygon for which I have a body. So all that I have done through this overriding is the fact that the virtual function draw in polygon is no more pure. It is an implementable function. So polygon now becomes a concrete class. I can create an instance of a polygon. But similarly, when I inherit closed conics from shapes, I say, oh, I do not know how to draw a closed conic in general. So I do not override it. So what is inherited is this pure virtual function. So closed conics, even though it is not showing up here, but from inheritance, closed conics have a virtual function draw which is pure, which makes closed conics also an abstract base class. That is, I cannot have instances of closed conics created ever. Rest of the classes have all inherited and overridden the function. So they have changed the pure virtual function drawing shapes into non-pure virtual function with implementation, and they become concrete classes. So given this, now I can write a main routine where I create a collection of objects on the canvas. I do a new triangle. This creates a triangle. I do a new quadrilateral. I do a new circle. I do a new ellipse. And I initialize an array of shapes pointer with these pointers. So shapes ARR0 is a pointer to shape type, shapes class, but it actually points to a triangle class object, and so on. So now to draw, I can write a beautifully simple code. All that I do is I write a for loop. You'll see later on if we use vector and iterators on that, it will get even more compact. So I have to run through these objects, these pointers. So I start with an index 0, go up to the number of elements. So the next code is basically to find number of elements, which is size of the array divided by the size of every element, which is shape star. This will give you the number of elements. So that's how I will go. Plus plus I. So keeps on incrementing 0, 1, 2, 3. And on every pointer I do, I call draw. So what will happen on ARR0? The draw of triangle function will get called. What will happen on ARR1? Draw of quadrilateral function will get called. And so on and so forth. The beauty of this whole code is, think about it, does not matter what is the collection that you do, as long as you create objects which come from some class that is inherited from shape on this RR. This code will perfectly work. This draw code on the canvas will perfectly work. What is even more interesting is if tomorrow you specialize from quadrilateral and have a rectangle class, you say class rectangle colon public quadrilateral, and define and override the draw function for rectangle, then you will not need to change this code at all. Everything will work as it were. So kind of here what you are doing is you are kind of dispatching your function called draw based on the dynamic type of the object. So this is called a type switch. You are doing a switching of which function to call. Of different function pointers when we introduced function pointers for implementing calculator. Here, you are doing that quite implicitly and in a quite extensive form. I'll go back one slide to slide 9 to tell you what I have already told. So a class containing, so I'm on slide 9, module 28. So a class containing at least one pure virtual function is called abstract base class. You understand that now. Pure virtual functions may be inherited or defined in the class. If you do not overwrite, then you inherit the pure form. No instance can be created for abstract base class, quite obviously, because on that instance, you would not have been able to invoke the pure virtual function. It naturally, since you cannot create an instance, an abstract base class does not have a constructor or destructor. An abstract base class, however, may have other virtual, non-pure, and non-virtual member functions as well as data members. Everything else it can have. It's a model which generically applies over the whole hierarchy, but you just cannot construct, just cannot instantiate it ever. The data members in the abstract base class should be protected, of course, though private and public will also be allowed. Now, normally it should be protected because you don't expect that since abstract base class will not have an instance, so it is difficult to justify what the private members will do, but you are allowed to do it. Member functions in abstract base class should be public, though private and protected members are also allowed. A concrete class must override and implement all pure virtual functions so that it can be instantiated. Here we have shown in terms of one pure virtual function, but that can be extended to multiple. So this was the example that we saw. I'm going to slide 11. So this is, if you run this code, then this is the output that we get. And note that instances for class shapes and class cannot be. Now, here I would put another twister to say that a pure virtual function optionally may have a body also. A pure virtual function may have a body. That having a body does not take away the purity of the pure virtual function. It still remains pure virtual function by this, but it is allowed to have a body. Now, you might question as to why would you like to have a body for a pure virtual function. The reason often is in terms of the hierarchical design. For example, let's say in shapes, I give a body to this pure virtual function, knowing fully well that shape can never have an instance, and that since it will never have an instance, there will not be an instance to call this. But in the overridden functions, in each one of them, I can actually call it. So what I can do with this is the fact that I do not know in which order this drawing is going to happen. And therefore, there may be some graphic system initialization, brush selection, color selection, and all that can happen, that may need to happen. So this will be a very nice way to put all that common code at the root, right? Because it is all inherited from here. So it is a very good programming practice that the code that may be common between all virtual functions which are overridden from this pure virtual function can be put in a reuse model by putting it as a body of the pure virtual function. Okay? So this is what is possible to be done. If you do that, slide 13, you will see in the output that every time we are calling the respective draw function, it first calls the draw a function of shape and shows that. Though it continues that even with the body, no instance of class shape or the derived closed convex class which has not overridden draw, no instance of them can be created. I would like to put a caution here is the compilers are non-uniform in terms of this support for the body for a pure virtual function. I've shown here in terms of in situ declaration. Many compilers don't support that. If your compiler does not, then you don't have to panic and think that this is wrong. Just all that you need to do is to define the body outside of the class. So just terminate this with equal to 0 semicolon, and then you write void shapes colon draw parenthesis and the body externally, and that will work. So it's a compiler idiosyncrasy that you have. So we have discussed this two very key concepts besides static and dynamic in terms of virtual destructors and pure virtual function and abstract base class. Let me stop here and see if we have any questions at this point.
Excuse me, sir.
Yes, please.
So I have a doubt. So in the
Yes.
abstract base class, if there are more than one pure virtual function, and I
Yes.
create a derived class which overrides only one of the virtual functions, so will
Then the
the
derived class continues to be an abstract base class.
Okay, so we cannot instantiate the derived class.
Obviously, and see, the logic is very simple. If you what you're saying by saying that a function is purely virtual, you are saying that I do not want to talk about its implementation. So even if a class has one pure virtual function, you cannot have an instance of that because that instance would have invoked that pure virtual function. So if your abstract base class has two pure virtual functions, the derived class has to override both of them in a non-virtual manner. Only then it will become a concrete class. Are you getting me? So I could have one base class having two pure virtual functions. Derived from that, another class which has overridden one with a non-pure virtual function, but has not overridden the other. So it still remains to be an abstract base class. Then I have another class which is derived from this, which is making that other pure virtual function in terms of a overridden non-pure virtual function. Then this third class only becomes concrete. Right. So if you keep this in mind that you cannot invoke an pure virtual function because I'm saying that I do not want to talk about set implementation. Right. So it becomes very easy to understand.
Okay, sir. Thank you.
Any other question? No? Okay. Then let me stop here. We will continue on the dynamic binding on this polymorphism, and what I'll do tomorrow is take an extensive example of a organizational hierarchy and show you for a very simple problem of processing of salary, if you have to write it in C, what kind of solution you will have. If you have to write it with a non-polymorphic hierarchy, what kind of solution you will have. And with a polymorphic hierarchy, what kind of beautiful, compact, extensible solution you have. So that you have a complete practical feel of how to practice this core principle of object orientation, which is in terms of inheritance and particularly polymorphic hierarchy. Thank you very much. Have a good day. See you tomorrow at 8 in the morning.